Right, so this video is on chapter 10. We're starting a new chapter, and it's the last main chapter for this year on probability. So we're going to do some probability, and then we'll start a little bit of chapter 11, which is on statistics, but the main focus right now for the next few weeks is to finish up probability for this class. So probability is a field that deals with chances of things happening, and it leads into statistics as well. It's kind of this preparation for if you're doing applied math or AP stats next year. This will set you up for the things that you need for those classes, as well as just prepare you for probability of stats in general, which even if you don't do applied or AP stats next year, you will probably have to do a class on it in college, or at some point it's still a good idea to understand how to look at probabilities and data and understand it, because that's something that shows up in everyday life a lot. Like when you read the newspaper and see studies and polls and stuff that they talk about. So for probability, we're going to start off in this first section looking at basic probability and sample space. So some of this stuff should be familiar to you from last year. If you did geometry, you've done some probability then. So hopefully it'll be a review. And for some of you who didn't do that or might have forgotten, then this will be the first time you see it, but hopefully it's still easy enough to follow along. So probability is really just the number of things, the number of chances of something that you want happen. So the number of times the outcome you want happens, divided by the number of total outcomes you could have had. So a sample space is the set of all the outcomes you can have from something, set of all outcomes. So for example, let's think of a situation where we're going to roll a six-sided die and flip a coin. We want to know how many possible outcomes we get from that. So to do this, we use something called a tree diagram, where we start off with just one dot, that's our starting point, and we're going to do the first thing, which is roll a dice. So when I roll a dice, I can get 6 different things. I could roll a 1, I can roll a 2, I can roll a 3, 4, 5, or 6. After I roll my dice, I'm going to flip a coin. Every time I flip a coin, I can get heads or tails. So each number gives me either a heads or a tails after it. So in total, I can get a 1 in a heads, a 1 in tails, 2 heads, 2 tails, 3 heads and then 3 tails, or 4 in a heads, or 4 in then tails, 5 in heads and 5 in tails, 6 in heads, 6 in tails. The tree diagram is just a way for me to list out all these possibilities in a way that helps me not miss anything and helps me organize all of that. Or you can also list out sample spaces in a list like this. Either one is fine. This is a way to list all the outcomes. So the probability would be number of desired outcomes, or the outcomes you want, divided by the number of total outcomes, the sample space size. To write a probability of something, we use capital P to mean probability, and we put parentheses around the thing that's happening. So the probability of rolling a 1, for example, would be probability of A, where A is rolling a 1. These things are called events, the thing that's happening, the desired outcome, and we write it as P of A. So let's do an example. The probability of rolling a number bigger than 5 and then flipping heads. So this is the probability of rolling 5 and then getting heads. Rolling bigger than 5, number bigger than 5, and a heads. So if we look at my sample space, I need to be flipping heads and I need to roll a number bigger than 5. So bigger than 5, well, that has to be 6. And flipping heads, well, that's that one thing. So I have one outcome that's desirable. And then the total outcomes was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have a 1 out of 12 chance to roll a number bigger than 5 and flip heads. Usually when we do probabilities, we can either write them as fractions like this or as decimals. Generally for the online stuff, the decimal is probably going to be more used, especially when you're typing it in. So 0.08 would be the probability of that, which means about an 8% chance. The other thing we can do is called the complement. So the complement of an event is the probability that the event does not happen. Probability that the event does not happen. So we write this as probability of the event, and we put a little bar on top, which means complement. And the way we calculate this, so all probabilities of things exist in the space that totals up to 1. Something has to happen. We don't know what that something is, but something's going to happen. Either it's a thing we want or it's a thing we don't want. When something has to happen, that's a probability of 1. There's a 100% chance of something happening. And so the probability of the complement of something not happening and the probability of something happening together will equal 1. So anytime you want to calculate the probability of the complement, it's 1 minus the probability of the event. Or if you want the probability of the event, you can do 1 minus probability of the complement. So now we look at another example. We want the probability of rolling a number less than 6 on the dice and getting heads or tails. So if I go back to my sample space, so less than 6, there's a lot of these, right? There's the 5 tails, 5 heads, 4 tails, all of those things. So I can either just count all of that up. And if I count all of that up, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So probability of rolling less than 6 and then getting heads or tails would be 10 different outcomes out of 12. Or I can do it using the complement. I can say, what's the probability of not doing this? What's the probability of rolling a number that is greater than or equal to 6 and then getting heads or tails? Well, in this case, there's only 2 places where that happens. 2 out of 12. And so then this is the complement. This is P of A complement. This is P of A. And if we look at these two numbers, 10 out of 12 plus 2 out of 12, that equals 1. So instead of having counted 10 things, I can also say the probability of A is 1 minus 2 out of 12, which is 10 out of 12. And calculate that probability. The decimal is 0.83. So sometimes you want to calculate probability of the complement. Sometimes you want to calculate probabilities of straight up events. In this case, it was easy to do the first thing because I had already written out the sample space. But if I hadn't written out that full sample space, it would probably be easier to do the second one where I only have to count 2 things rather than counting 10 different things. So let's do an example where we're not going to list out the whole sample space at the beginning to see where the complement will be more useful. So we have 2 bags. Each of them have 10 tiles in them, numbered 1 through 10. So there are 100 possible outcomes we can get if we take a tile from each bag. The first thing we want to see is what is the probability that the sum of the 2 tiles that we pick is not 10. So if I wanted to calculate all the times where it's not 10, that's a lot of different numbers. I can have 1 plus 1, I could do 1 plus 2, 1 plus 3, 1 plus 4, and so on. So instead, I'm going to take the complement, which would be the probability that the sum is 10, and calculate all of these outcomes. Well, if I draw a 1 from the first bag, then my second tile has to be a 9 to equal 10. If I draw a 2, the second thing has to be an 8. If I draw a 3, it has to be 7. 4 has to be 6. If I draw a 5, I have to get 5. If I draw a 5 from the other bag, I have to get 5 again. If I draw a 6, I can get 4, 7 and 3, 8 and 2, 9 and 1. So there are 10 different outcomes that come out of this, where they equal 10. So here I counted 10 things. If I did it the other way around, I would have to count 90 different things. And so it's much faster to do it this way. So this probability is 10 out of 100, which is 0.1. So the probability that I actually want, where the sum is not 10, would be 1 minus this complement, which would be 0.9. So this is where using the complement helps a lot, because then you don't have to count 90 different things. You only had to count 10 different things. Similarly, on this next one, now we want the product to be greater than 10. So we'll do the complement, where the product is less than or equal to 10. If you need to decide on your own which one to use, the complement or the event, you try listing out a few of them on your own to see which one seems like you'll have to count more of, and then pick the one where you have to count less. You won't always guess that correctly, and that's why it doesn't matter which way you do it. You'll still get the correct probability at the end, but sometimes you'll kind of notice, if it's meant to be a complement thing, if you were doing it the other way around, you'd probably have to pick 90 different things versus 5 different things, something like that. So it'll be pretty obvious which one you should be counting once you start counting a few of them. So in this case, you have product will do the complement less than or equal to 10. So if I pick a 1 from the first bag, then I can pick a 1 from the second bag, a 2, 3, 4. I can pick any other number from the second bag because all of them, when I multiply it to 1, is going to be less than or equal to 10. So I get 10 different things if I choose a 1 from the first bag. If I pick a 2 from the first bag, then I can do up to 2 times 5, which will give me 10. If I do 2 times 6, that's too big. That's 12. That's bigger than 10. So I get 5 different outcomes from picking 2. If I pick the 3 first, go 3 times 1, 3 times 2, 3 times 3. 3 times 4 is too big. 4 would be 4 times 1, 4 times 2, but then 4 times 3 is too big. 5 would be 5 times 1 and 5 times 2. 6 would give me 6 times 1, but then 6 times 2 is too big. 7 would give me 7 times 1, and then 7 times 2 is too big. 8 is only 1 time. 9, only 1 time. And 10 can only go once as well. So in total, I have 10 plus 5, 15, 18, 20, 22, 23, 24, 25, 26, 27 outcomes that I want, divided by the 100 total outcomes. And so then the probability I actually want, where the product is greater than 10, would be 1 minus this 0.27, which would be 0.73. So again, this is where complements help. We don't have to count as many things. Even in this one, even counting the complement was a lot. We had to count 27 different things, but that's still less than counting 73 different things. And so it's just a matter of doing a lot of counting in problems like this, listing things out, try to find a way to keep that listing organized, like keep a table like this or do a tree diagram, but some way to help you just make sure that you're counting everything and not missing out on something. The next idea in this section is theoretical probability and experimental probability. So all the things we've done so far, those are theoretical probabilities. We're not actually doing this in real life. We're just imagining these scenarios and thinking about all the possibilities. So this is in theory, what should happen. What should happen. So this is based on knowing the situation, the number of desired outcomes, versus divided by all the possible outcomes. Right, this is theoretical. But theory and real life don't always match up, especially in probability, they don't match up. Probability is trying to get to what happens in real life, but it's still guessing what's happening. A lot of times we can be good about our guesses, but not always perfect, and this is where that difference is going to show up. So for example, think about flipping a coin. Theoretically, the probability of flipping heads is 50%, and the probability of flipping tails is 50%. If you only flip 2 coins, you could get 1 heads and one tails, and that would make our probability work out. It would be 50 and 50. But you could also get 2 heads or you could get 2 tails. And then you don't have a 50-50 split. You have either all heads or all tails. And that's still possible. It doesn't mean that our probabilities are wrong. It doesn't mean that the probability of heads and probability of tails isn't 50%. It just means that in that one instance you did it, you got a different outcome. And so the experimental probability is calculated by the number of actual successes you get divided by the number of times you try, number of trials. So let's kind of see how this works. So I have a simulator here that is going to flip coins for us. So we're going to flip 10 different coins. Theoretically, we should get 5 heads and we should get 5 tails. So let's flip it. In this case, we got 7 heads and 3 tails. That's very different. If I only did this one test, I would say the probability of getting heads is 70% and the probability of getting tails is 30%. Experimentally, that's what happened. But if I flip again, well, now I get 6 heads and 4 tails. So now it looks like the probability is 60 and 40. If I flip again, now I got 2 heads and then 8 tails. So now that's a 20-80 split. So as you can see in these experiments, the probabilities change a lot. These experimental probabilities are very different from the theoretical probabilities. If I did this enough times, right, like if I flip this like 100 times, then I'd probably be closer to 50 and 50. Now I can't really count all of these, and it doesn't really tell me. But you could imagine like if I do this a lot of times, that's where the probabilities start matching. Experimental probabilities look like theoretical probabilities when you do a lot of them. So if you flipped a coin 1,000 times, you would probably get 500 heads and 500 tails. You'll still get some variation. You could get like 498 heads and 502 tails. But it's very unlikely at that stage to get something like what we got, where you only get 1 heads and 999 tails. It's still possible, very unlikely. And that's kind of where probability and statistics kind of mesh up to think about how likely is that outcome going to be. Very unlikely. But hopefully you see the difference between experimental and probability. When the trials get really big, when the trials go up a lot, then these start looking the same. Looking the same. But in small numbers, these can be very different. Sometimes we just don't have a way to think about it theoretically. So like on this one, I have 30 students take a test. 8 got A's, 13 got B's, 9 got C's. If I pick a random person from this 30-person class, the probability that that person got a C, I can only get that based on this experimental data that I have. I have 9 out of 30 people have C's, and so the probability that someone got a C is 9 out of 30. Right, the probability of the C is 9 out of 30. I'm using real data that I have, rather than like thinking about if 30 students take a test and there are 3 different letter grades I can give. It's not that 10 people got each grade. What's the probability that a student got either an A or an B? This one I have 2 different ways to do it. I can either say the probability of A or B is getting 8 plus 13 divided by 30, so 21 out of 30. Or I can do it with the complement. If they're getting an A or a B, that means they didn't get a C, which would be 1 minus the probability of getting a C, which is 1 minus 9 over 30, which is also 21 over 30. So both ways work, and you can always pick which one you want. Sometimes it's easier to pick one or the other. The last kind of probability is called geometric probabilities. This is when you have shapes and you're looking at areas of shapes or lengths and distances to think of probability. And this is really just the area of the shape you want divided by the total area. So if we have a dartboard that has this design on it, it has a circle and then a triangle on the inside, we want to know what's the probability that if we throw a dart at it, the dart is going to land outside the circle. So we want to know what the total area of the shape is, which is a square. We know that the radius of the circle is 4, which means this side is also 4. So the side length is 8. So the area of the square is 8 squared, which is 64. And we want to know the area of the circle, which would be pi r squared. So pi times 4 squared is 16 pi. And we want to know what the probability it doesn't land in the circle. That's a complement. So instead, let's find the probability it lands in the circle. So area of circle divided by total area. And then that's going to be pi over 4. And then we'll do the complement. Probably it doesn't land in the circle is 1 minus that. And we get this probability. So that's our introduction into thinking about probabilities. We have a few different ways to do it. We have thinking about sample spaces and counting things. For theoretical probabilities, we have experimental probabilities where we do an experiment and just count up how many times we got the outcome we wanted. And then geometric probabilities, where we have shapes and look at the areas of shapes to decide. For the geometric probability, area formulas will be given to you, so you don't have to memorize them for now. So if you forget how to find the area of a shape, you'll be able to get that information. But mostly we want you to just get the idea of thinking about total area, total outcomes, and then the specific outcomes that you want.